Okay, welcome everybody to another video. Last time we made this important observation that if K is an extension of F, then it is also a vector space over F. And in mathematics, it is almost always the case that when you can treat a given object in two different ways, then you gain insights into its properties. So in this case, of course, when we have a field extension, we can treat it one as a field extension, and on the other hand, we can treat it as a vector space. So we can really hope for some good information to be gleaned from this. So let K be a field extension of F. Then, as we discussed in the previous video, then K is a vector space over F. So we can talk about the dimension of K over F. So we'll make the following definition. If K is a finite dimensional vector space over F, which means that K has a basis that consists of finitely many elements over F, then K is called a finite extension of F. So an extension in which the bigger field is a finite dimensional vector space over the smaller field is called finite extension. The dimension of K as a vector space over F is called the degree. Of K over F, denoted by K column F. As you may have already noticed, in abstract algebra, people behave as if there are only 5 or 6 words in the world, and they keep calling different things by the same names. And I understand if this gets a little confusing. There are a few things that are called degrees. There's the degree of the polynomial. Now you have the degree of the extension. There's also something called the degree of an algebraic number, which I decided not to use, to just not introduce a third thing that is called a degree. But here I will use the word degree because this is definitely a very standard terminology. So an example, what we already know from the previous videos, is that the degree of Q adjoin cube root of 2 over Q is 3. And on the other hand, we also computed the degree, oh, I'm sorry, we don't know that it's 3, it's just less than or equal to 3. In the last video, we found out that 1 cube root of 2 and cube root of 2 squared is a spanning set for Q adjoin cube root of 2 as a vector space over Q, but we don't know at this point that this set is linearly independent. So all we know is that the dimension, so the degree, is less than or equal to 3. But then we also did another example, Q adjoin radical 5 over Q, and we actually got that the degree here was 2. One of the important things for us is to be able to compute degrees of various field extensions. And this would be a big nuisance if whenever we actually get to a point where we know that we have a spanning set, but are not able to say if the spanning set is a basis, then we would only get inequalities. Let me give you another example. So consider this. Q adjoint zeta 3. This is a field where we adjoin the cube root of unity. So the cosine 2 pi over 3 plus I sine 2 pi over 3. And this, we discussed this in one of the earlier videos, that you only need powers of zeta 3 up to a square, because the cube power, the third power of cube root of unity is 1, so then you can subsume that thing into the first coefficient and so on. Just like in this example we did with cube root of 2, you never need any power higher than the square of zeta 3. However, so from this, what we can only say is that the degree of Q adjoint zeta 3 over Q is less than or equal to 3. I don't really know at this point if this is an equality. So let's state a theorem that is going to actually help us with answering these sort of questions. So, theorem. Let K be a field extension of F and let alpha in K be algebraic over F. Then F of alpha is a finite extension of F, and the degree of F of alpha over F is equal to the degree of the minimal polynomial of alpha over F. Now this is very useful. As you have already seen, computing the degree of computing the minimal polynomial is often not an easy thing. But once you have done it, this actually helps you with the degrees, because this now immediately answers all these questions here. So let's look at an application of this theorem to these examples, and then we prove it. So in the example below, we had that the degree of cube root of Q adjoint cube root of 2 over Q is at most 3. However, what's the minimal polynomial of cube root of 2 over Q? Well, you know that that's x cubed minus 2. How do I know that? In one of the previous videos, we saw that if you have an irreducible polynomial, which is monic and has coefficients in Q, then that is the minimal polynomial of your element. I mean, if the element is a root of this polynomial. So cube root of 2 is a root of this polynomial. The polynomial is monic, has coefficients in Q, and is irreducible. So that means this must be 3. Okay? That 3 here is that 3 here. It's the degree of the minimal polynomial. This also gives us, it confirms this observation that we already made, that it's 2, because I know the minimal polynomial of radical 5 It's x squared minus 5. Again, it's an irreducible polynomial, has coefficients in q, has radical 5 as a root, and is monic. So it's the minimal polynomial of radical 5 over q. So this degree must be 2. Again, that's the 2. Finally, let's answer the question about this last example. What is this? Okay, so I need the minimal polynomial of cube root of zeta 3 over q. And when we discussed minimal polynomials, we said that sort of the obvious thing that comes to mind is the polynomial x cubed minus 1. However, that is not the minimal polynomial because it's not irreducible over q. In fact, when you go back to this video, you'll see that the minimal polynomial of cube root of unity, the zeta 3, which is cosine 2 pi over 3 plus I sine 2 pi over 3, the minimal polynomial of that zeta 3 over q is x squared plus x plus 1. So that means this degree is actually 2. It's not 3. Right? Note the difference. It's actually not 3. Which means, as a consequence of this, I know that I do not have to use zeta 3 squared. Okay, in fact, let me just add to this theorem one other very useful thing. Namely, this theorem also gives us a basis. So this is the degree of the minimal polynomial. Furthermore, the set 1 alpha, alpha squared, alpha to okay, so I need the letter for this degree. Let's say that the degree of the minimal polynomial will be d is a basis. Of f alpha over f. Okay, so if I call d the degree of the minimal polynomial of alpha over f, then this is the degree of the field extensions equal to the degree of the minimal polynomial. And secondly, this is a basis. It's a basis. There are many other possible bases, but this in particular is a basis. So that means I have now bases for all these field extensions, for all these examples here that I wrote down. So I'm just going to add this on here. So for this example, basis would be 1 cube root of 2 cube root of 2 squared, which was our spanning set, right? My alpha here in this case is cube root of 2. My f is q. Degree is 3, and the basis is 1 alpha alpha squared all the way up to the power 1 less than the degree of the minimal polynomial. The degree of the minimal polynomial is 3 in this case, so I go all the way up to 2. Here, the degree of the minimal polynomial is 2, so I use 1 and radical 5 to the power 1, and I stop, right? Because 1 is 1 less than 2, which is the degree of the minimal polynomial. And similarly here, it's 1 zeta 3 to the 1. Okay, the degree of the minimal polynomial is 2, so I stop here. Because I always stop at 1 less than the degree of the minimal polynomial. Okay, let's prove this theorem now. It's a very useful theorem because it allows us to use our knowledge of minimal polynomials to conclude something about the degrees. So let's prove the theorem. Proof. Note that it is enough to prove that 1 alpha alpha squared alpha to d minus 1 is a basis. Oh, so look, what I'm saying is it's actually enough to prove this last sentence of the theorem, and everything else is implied by this last sentence. Let's check that. Okay, well, if I prove that this is a basis, then how many elements do I have in that basis? Finitely many or infinitely many? Well, finitely many. So that would mean that f adjoint alpha has only a finite basis over f, so it's finite dimensional as a vector space over f. So that means this will prove that statement. F of alpha is a finite extension. That means finite dimensional over f, because I have a finite basis. Secondly, exactly how many elements do I have in this basis? Well, 1, 2, 3. Oh, with this one, actually I have d, right? Because I start with sort of the 0th power here, and I end with the power d minus 1. So I have exactly d elements. And the number of elements in the basis is equal to the dimension. So that means this dimension here is equal to exactly d. Okay, d is the degree of the minimal polynomial. Maybe let's just write that, where d is the degree of the minimal polynomial of alpha over f. So in fact it's just enough to prove that that set that I wrote down here, this one, is a basis. How do you show that something is a basis? You show that it spans and that it's linearly independent. So let's write down, so let f equal x to the d plus a d minus 1 x to the d minus 1 plus dot 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 plus a1 x plus a0 be the minimal polynomial. Remember, the minimal polynomial is unique, so I can write the of alpha over f. Oh, maybe one thing to mention here. How do I even know that alpha satisfies any polynomial over f? How do I know that it has a minimal polynomial? Well, because it's algebraic. And all the algebraic elements satisfy some polynomial with coefficients in f. Dividing by the leading term, I know that I get a monic polynomial. So alpha does have a minimal polynomial. Every algebraic element satisfies a minimal polynomial. Okay. So I need to show two things, right? So we first show that the set spans f of alpha. What is f of alpha? F of alpha, oh, I shouldn't use the a0 and a1 now, so I'm going to use b's. So b0 plus b1 alpha plus dot 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 bn alpha to the n, where bi's are in f and n is any non-negative integer. So that means what I have to show is that every such expression, no matter how big n is, can be written using just powers up to d minus 1. That's what it would mean that this set spans. If every such expression, no matter how big n is, can be written just using these powers, then that means that these powers span. Okay, so I'm gonna, of course, everything up to the power d minus 1 here can be written using powers up to d minus 1. That's just a tautology. So the first one, the first power for which this isn't clear, is the power alpha to the d. So let's show we can write alpha to the d using only 1 through alpha to the d minus 1. Well, how do I do that? Remember that alpha is a root of this polynomial. We have f of alpha to be 0. This polynomial, when I plug in alpha, I get 0. So what is that polynomial when I plug in alpha? That's alpha to the d plus a d minus 1 alpha to the d minus 1 plus dot 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 plus a1 alpha plus a0. Right? That is nothing else, just f of alpha. This is what I get when I plug in alpha to f. And that's 0. So note, by taking everything else to the other side and leaving alpha d on one side, I get that alpha d is equal to minus a d minus 1 alpha to the d minus 1 minus dot 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 minus a1 alpha minus a0. Look, what have I done? I wrote alpha to the d using only the powers of alpha that are less than or equal to d minus 1. So that means I can express alpha to the d by the lower powers. How did I do it? By using the fact that alpha satisfies this polynomial. Okay, well, can I then write alpha to the d plus 1 using only the lower powers? Yes, it's slightly more complicated, but I can still do it. Let's show that. So let's show we can write alpha to the d plus 1 using only 1 through alpha to the d minus 1. How would I do this? Well, I look at this. Let's call this expression star. And I multiply both sides of star by alpha. Both sides of star by alpha. What do we get? On the left-hand side, we get alpha to the d plus 1. What do we get on the right-hand side? We get minus a d minus 1 alpha to the d minus a d minus 2 alpha to the d minus 1. Right? I didn't have this written here. That was in the dots, but I'm just going to write it here now. Minus dot 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 minus a1 alpha squared minus a0 alpha. Have I achieved what I wanted?